In this video, we will be demonstrating an IoT-based monitoring system for dynamic VDD-drop inside an IC. The first part of this video will cover the overall system architecture. We split the system architecture into user domain, cloud domain, and edge domain. There are 3 edges so far under our edge domain. This system allows users around the world to monitor the power supply and temperature status of an IC in any location through our IoT network. User domain refers to the personal devices with our software that links to the cloud domain, where cloud domain is the workstation located in our lab. At last, edge domain includes any item we wish to observe with our monitoring IC implemented. Now we introduce each device in our edge domain. First, the printed circuit board that carries our PIPTA IC, FPGA that controls the timing sequence, and the linked one used as the sensor hub. The IC used in this monitoring system is designed and created by our lab. Our monitoring IC can capture any kind of dynamic VDD drop on the power supply path, even if the dynamic VDD drop occurs within 1 nanosecond. We also use a temperature compensation method that helps us estimate the VDD drop more precisely. VDD drop within 1 nanosecond is actually quite hard to be realized, where we had to use high-resolution time-to-digital circuit in order to accomplish it correctly. We implemented 16 monitoring devices in the circuit that we taped out. It grants us the ability to monitor the supply voltage and temperature around it. The phase lock loop used in the monitoring system is created using the compiler designed by our lab. We have made the power ring of the IC thinner than usual, so the bad performances can be captured by our monitoring device. Our monitoring IC will need to go through a calibration process first, once it is taped out from fab. The purpose of this calibration process is to fix the variance of the IC caused by process variation. The calibration data will be uploaded and recorded in our cloud domain, which is used to support the monitoring process later on. Now we demonstrate our monitoring system in real time. First, we have located our 3 different edge devices into different locations, where edge A is on the grass without any shelter. Edge B is on the rooftop with cool temperature. Edge C is in our lab. After turning on each edge device, their raw data will be gathered without intruding their function. Then the raw data will be sent to our cloud domain, converted into VDD drop and temperature information, then will be recorded. Let's see the result from edge A. First, the average VDD drop. We can see that the average VDD drop over 16 monitoring device is around 2 mV to 4.1 mV, which is around 0.4%. The worst VDD drop is around 107.1 mV to 207.8 mV, meaning that the worst VDD drop can get to as high as 20.8%. The other 2 edge devices share a similar situation. From these observations, we can tell that abrupt high VDD drop can happen even when the overall average condition is fine. About the temperature monitoring part, we use the temperature compensation method to estimate the temperature of our 3 edge devices. To verify the accuracy of our monitoring system, we also implemented an extra thermometer to report the environment temperature. We started our observation from 1:30 p.m. to 5 p.m. and report data in every 15 minutes. At last, we take the average temperature from 16 different monitors and created a graph based on it. We can see the temperature of edge A can get as high as 54.4 degrees due to the exposure to the sun. Then the temperature decreases as the sun goes down. While edge B doesn't have such high temperature variance since it's located in a relatively cool place. And edge C has the least temperature variation because it is inside the lab where the temperature is consistent. We can see that the temperature reported from our device is very close to the temperature sensed by the thermometer, which shows the good accuracy of our monitoring system. Thank you for your patience. The demonstration of IoT-based monitoring system for dynamic VDD drop inside an IC ends here.